Welcome to this discussion regarding large language models. Large language models, LLMs, are advanced artificial intelligence systems designed to understand and generate human language. They power applications like chatbots, content creation tools, translation services, and research assistants. Unlike traditional rule-based language programs, LLMs learn from vast amounts of text data and recognize patterns, enabling them to generate natural-sounding and contextually relevant responses. LLMs are built on deep learning, a subset of machine learning that enables them to learn from text at an enormous scale. They do not have inherent knowledge or reasoning abilities. Instead, they predict and generate text based on learned patterns. This prediction ability, combined with a sophisticated neural network structure, allows them to produce text that can sometimes feel indistinguishable from human writing. One of the fundamental capabilities of LLMs is pattern recognition, the ability to identify linguistic structures, relationships between words, and statistical regularities in text. Rather than memorizing information, they learn by detecting trends in how language is used. LLMs recognize language patterns at different levels. First, word co-occurrence, words that frequently appear together. For example, machine learning is more common than machine elephant. Second, syntax and grammar. They infer grammatical rules by analyzing sentence structures. For instance, subject-verb-object order in English. Third, semantic relationships. Words have contextual meanings. For example, Paris relates to France in a similar way that Berlin relates to Germany. Lastly, discourse coherence. They recognize how ideas connect across multiple sentences, enabling them to generate coherent paragraphs and long-form text. LLMs learn by training on massive datasets that include books, articles, and other textual sources. The process follows several stages. First, data collection. The model is exposed to diverse text sources to develop a broad understanding of language. Second, tokenization. Text is split into smaller units called tokens, words, subwords, or characters that serve as the building blocks for training. Third, training with self-supervision. LLMs learn by predicting missing or next words in a sentence, adjusting their internal representations based on the correctness of their predictions. Lastly, fine-tuning. The base model is refined using specific datasets or reinforcement learning to align it with human values and practical applications. The backbone of modern LLMs is the transformer architecture, introduced in the 2017 paper Attention is All You Need. Transformers revolutionized natural language processing, NLP, by allowing models to analyze entire sequences of text in parallel rather than sequentially. Since computers do not understand words like humans, LLMs convert words into numerical representations called word embeddings. These embeddings capture the meanings of words by placing similar words close together in a high-dimensional space. For example, in an embedding space, king and queen have similar vectors because they share semantic meaning. Apple is in a different region because it belongs to the category of fruits rather than royalty. Unlike older models that assigned fixed word embeddings, such as word2vec, transformers use contextual embeddings, which adjust based on the sentence. For example, bank has different meanings in different sentences. I deposited money in the bank. Here the bank is a financial institution. I sat by the riverbank. Here, bank is a land near water. Transformers ensure that the word bank takes on different representations depending on context, improving accuracy in text generation and comprehension. A crucial innovation of transformers is the self-attention mechanism, which allows LLMs to weigh the importance of different words in a sentence, regardless of their position. Consider the sentence, "The cat, which had been stuck on the roof for hours, was finally rescued by the firefighter." A traditional model might struggle to link cat with rescued due to the long sentence structure. However, The self-attention mechanism ensures that the model correctly associates cat as the entity being rescued, improving comprehension. Unlike older models that process text sequentially, like RNNs, transformers analyze all words simultaneously. This parallel processing allows them to handle long-range dependencies, making them highly efficient in dealing with complex texts, novels, and research papers. For example, if a novel introduces a character in Chapter 1 and references them in Chapter 20, the transformer architecture enables the model to retain and recall relevant details, improving coherence in long-form text generation. BERT, introduced by Google in 2018, is a transformer-based model designed specifically for natural language understanding. Unlike traditional transformer models, which were often used for sequence-to-sequence tasks like machine translation, BERT is designed for tasks such as question answering, sentiment analysis, and text classification. BERT differs from previous transformer-based models in three key ways. First, it only uses the encoder part of the transformer. No decoder is needed because BERT is focused on understanding, not generating text. Second, it is bidirectional, meaning it learns from both left and right context simultaneously. Third, it is pre-trained on large amounts of unlabeled text and fine-tuned for specific NLP tasks. While BERT is built on the Transformer's encoder stack, it introduces key modifications. Traditional transformer models like GPT, Generative Pre-trained Transformer, process text in a left-to-right fashion. BERT, on the other hand, processes text in both directions at the same time. This enables it to understand sentence meaning more deeply. For example, the man went to the blank to withdraw money. GPT predicts words based only on previous words, but BERT considers both previous and subsequent words to predict bank more accurately. During training, BERT randomly masks words in sentences and learns to predict them based on surrounding context. Consider this example, the dog blank over the fence. BERT learns to predict jumped by analyzing both left and right words. BERT is trained to determine whether one sentence logically follows another. This is known as next sentence prediction. Consider this set of sentences. Sentence A is, I love hiking in the mountains. Sentence B is, the weather today is sunny. This is unrelated to sentence A. Sentence C is, it gives me a great sense of adventure. This is related to sentence A. BERT is trained to classify whether sentence B or C follows sentence A more logically. BERT outperforms traditional transformers for natural language processing in several aspects. First, better contextual understanding. The bidirectional approach allows BERT to better understand sentence meaning, unlike left-to-right models. Second, pre-training on large datasets. BERT is pre-trained on massive text corpora such as Wikipedia, books, etc., and can be fine-tuned for specific NLP tasks. Third, general-purpose nature. BERT's pre-trained embeddings can be adapted for multiple downstream tasks, reducing the need for task-specific models. BERT extends the transformer's capabilities by focusing on understanding the deeper meaning of text rather than generating sequences. It refines the transformer encoder's ability to grasp bidirectional context, making it exceptionally powerful for NLP applications like search engines. Google Search uses BERT to understand queries better, chatbots and virtual assistants, text classification, named entity recognition, NER, and sentiment analysis. Large language models can be categorized based on whether they are primarily transformer-based or BERT-based, depending on whether they use the full transformer architecture, encoder-decoder or decoder-only, or specifically the encoder-only architecture of BERT. Examples of transformer-based LLMs are ChatGPT, Lame, and Claude. Examples of BERT-based LLMs include Roberta, robustly optimized BERT pre-training approach, and Distill BERT. In late 2024 and early 2025, China's DeepSeek introduced several significant enhancements to the traditional transformer architecture, aiming to improve efficiency, scalability, and performance in large language models. One of its features is multi-head latent attention, MLA. In a regular transformer, every incoming query, word, or token in a sentence is processed separately, and every piece of past information must be stored in memory. This is like a customer service system, where every conversation history is individually saved in large separate files, taking up a huge amount of storage space. DeepSeek introduced multi-head latent attention, MLA, which is like a smart call routing system that condenses past customer interactions into a summary rather than storing the full conversation history. Imagine each agent has a notepad where they jot down only the key points of past conversations instead of keeping a full transcript. When a customer calls again, the agent quickly reviews the key notes instead of scrolling through pages of past discussions. This makes it possible to serve more customers with less memory usage, just like how MLA reduces the storage required for long conversations in AI models while still remembering context efficiently. MLA compresses memory usage while maintaining accuracy, allowing models to process longer text without bloating storage or slowing down. Another outstanding feature is Mixture of Experts, MOE. A regular transformer treats every question as if a single agent must know everything. This is like having one generalist employee answering all kinds of customer service inquiries, whether it's about tech support, billing, or product recommendations. DeepSeek's Mixture of Experts MOE system is like having a specialized team of experts where only the most relevant specialists are called in for each query. Instead of one generalist handling everything, MOE dynamically picks a few experts who are best suited for each question. If a customer asks about billing, the system routes them to a finance expert instead of making a general agent figure it out. If the next call is about tech support, a tech specialist takes over. This allows DeepSeek's model to handle a huge volume of requests while using fewer resources, as only a small number of experts are actively working at any time. This leads to faster, more accurate, and cost-efficient responses. Multi-token prediction is another major enhancement. Traditional AI models predict one word at a time, much like a slow customer service agent who pauses after each word before deciding what to say next. Imagine asking a chatbot, "What's the best laptop for gaming?" Instead of answering fluently, it might respond like, "The best laptop for gaming is Asus ROG Zephyrus." This slow word-by-word processing makes conversation feel unnatural. DeepSeek changes the game by predicting multiple words at once, like a fast-speaking agent who can deliver full sentences instead of pausing after each word. Instead of saying, "the best laptop is," it quickly predicts an entire response. The best laptop for gaming is the Asus ROG Zephyrus due to its high refresh rate and powerful GPU. As a result, this significantly improves speed and fluency, making AI-generated text feel more natural and human-like. In DeepSeek, low-precision arithmetic can reduce unnecessary details to speed things up. Imagine a cash register at a store that calculates every total down to a millionth of a cent, even though rounding to 2 decimal places is enough for normal transactions. This excessive precision wastes processing power without providing extra value. DeepSeek optimizes this by using low-precision arithmetic, meaning it only keeps details that matter while rounding off unnecessary calculations. Instead of storing 12 decimal places, it rounds numbers intelligently, much like how humans say 9999 instead of 99876534235. This means the AI can perform calculations faster with less computing power. By doing so, the model runs more efficiently, consuming less energy and hardware power while maintaining accuracy. Further, DeepSeek employs optimized communication, It is like many agents working in parallel rather than one by one. Traditional models process information one step at a time, like a call center where each agent waits for the previous agent to finish before starting. DeepSeek overlaps tasks so multiple agents, or parts of the AI model, work simultaneously instead of waiting for each other. If one agent is writing an email, another can start analyzing the next customer request without waiting. This is like an assembly line, where different specialists handle different parts of a task at the same time, rather than one by one. This method reduces wait times and speeds up AI responses, making it more efficient at handling multiple tasks at once. DeepSeek's improvements make AI more powerful, cost-effective, and user-friendly, allowing it to process longer contexts, generate smoother responses, and run efficiently on large-scale systems. This makes DeepSeek a strong competitor in the LLM space, pushing the boundaries of transformer-based AI. No doubt LLM is a transforming technology that has many strengths. First, context awareness. LLMs generate coherent and meaningful text over long passages, maintaining context across multiple interactions. Second, scalability. Larger datasets and improved architectures enhance model performance. Third, creativity and adaptability. They can write essays, summarize books, generate poetry, and even compose code. However, although LLMs exhibit intelligent behaviors, it doesn't necessarily imply that they are really intelligent. They have certain noteworthy limitations. The first limitation is lack of true understanding. LLMs do not think or understand meaningfully. They only recognize statistical and probabilistic patterns. Second, if trained on biased datasets, models can generate biased outputs. Third, sometimes LLMs produce plausible but incorrect or fabricated information. This issue is known as AI hallucination. Last but not least, LLMs have no common sense. Humans possess embodied knowledge. We know what is sensible based on our experience. LLMs have abstract knowledge only, and thus on some occasions provided nonsensical advice due to their lack of embodied human experience. There are numerous real-world examples. For instance, roles like flight attendant, secretary, and physician's assistant are often linked to females, while roles such as lawyers and physical laborers are often associated with males. Further, in 2023, a lawyer cited several cases in a court filing, but those cases are fabricated by ChatGPT. Another notable example involves Google's AI search feature, which once recommended consuming at least one small rock per day. Large language models have transformed how humans interact with machines, enabling seamless and natural communication. While they excel at recognizing and generating language patterns, they do not possess true reasoning abilities or real-world understanding. DeepSeek's innovations, such as multi-head, latent attention, and mixture of experts, demonstrate that even within the transformer framework, significant efficiency improvements are possible. By achieving state-of-the-art performance at a fraction of the cost of models like ChatGPT, DeepSeek raises an important question. Are we approaching the limits of the transformer architecture, or will we need a fundamentally new paradigm to push AI even further? As AI research progresses, future models will aim for greater interpretability, factual accuracy, resource efficiency, and ethical alignment. While DeepSeek has shown that optimizing the transformer model can lead to substantial gains in efficiency, it also hints at the possibility that entirely new architectures may emerge, ones that go beyond self-attention mechanisms and introduce novel ways of processing information. This could pave the way for more new models, hybrid approaches, or even quantum-enhanced AI. Understanding how LLMs recognize patterns and generate language provides valuable insight into their capabilities and limitations, equipping us to use them responsibly and effectively. Despite their imperfections, LLMs continue to push the boundaries of artificial intelligence, shaping the future of human-computer interaction and redefining the role of AI in society. Whether the next breakthrough will come from refining transformers or replacing them altogether remains an open and exciting question. Thank you for joining me on this journey through the world of large language models. Now, I'd love to hear your thoughts. Do you believe LLMs will one day develop true intelligence, genuine comprehension, perhaps even self-awareness, rather than just mimicking intelligent behavior? Have transformer and BERT architectures reached their peak, or is there still untapped potential? And with innovative players like DeepSeek entering the scene, do you think we're on the verge of a paradigm shift toward a new kind of AI architecture? I'm all ears. Feel free to share your insights and reflections.